Oh, welcome to lecture 9.5 covering solving trigonometric equations. I am the only one in the room this evening, so hopefully I will answer all the questions that I can anticipate that you have. We'll go ahead and move forward. Okay, so the first thing that we come to in this section is the idea that because we can move through the circle, a unit circle, as many times as we'd like, and we know that the period of sine and cosine is both 2 pi. When we are coming up with possible solutions to trigonometric equations, we have to consider, if they're wanting all possible solutions, we have to consider that we may go through the circle more than just one time. So to compensate for that, when we find the solutions on the unit circle for that particular equation, what we're going to do is either add or subtract 2 pi k. All right, so 2 pi, that's going through the circle one time, and then k is just any integer. So that's just going to multiply you through the circle k amount of times. And we can go forwards or backwards. Now, we use this technique if we are not given a specific domain. So if it says exact solutions and there's no domain that you have to stay between, then you're going to add the plus or minus 2 pi k for sine and cosine. So let's go ahead and take a look. And we'll be using the unit circle a lot tonight, so I put one on just about every page. All right, so it says find all possible exact. They say exact because that means you're not going to go to your calculator and punch it in. You're going to use the unit circle to solve the equation. So all possible exact solutions for the equation cosine theta is 1/2. Okay, so let's look at the unit circle below. We know that the cosine of theta is the x value of the points on the unit circle. And so we're looking for x values that are 1/2. And we can see we have 1/2 here, and we have 1/2 here. So when theta is pi over 3, or when theta is 5 pi over 3, the cosine of those two angles is 1/2. So what that means is that theta had to be either pi over 3, but don't forget, maybe I'm going through the circle multiple times, so I need to add or subtract 2 pi k. Or theta can also equal 5 pi over 3 plus or minus 2 pi k. Those are all possible exact solutions for theta. Okay, now we'll look to the right here. We start out with the sine of t equaling 1/2. And we're trying to figure out, okay, well, what are the solutions for t? And so now we're looking at the y-coordinate that is equal to 1/2. And you can see that we have that at pi over 6. And 5 pi over 6. So here we get t is equal to pi over 6 plus or minus 2 pi k. T can also be equal to 5 pi over 6 plus or minus 2 pi k. All right, so pretty simple, just using the unit circle to identify those angle measurements. And those are given in radians. All right. So just moving forward through a couple more equations here. Looking a little more complex. So here we start out with 2 times the cosine of theta minus 3 equals negative 5. Well, what I want to do is I want to isolate the cosine of theta and see if I can identify where on the unit circle the cosine of that angle is equal to that value, just like I did on the other 2 problems. So I just need to isolate cosine theta. So the first thing I'm going to do is add, oops, I grabbed a white pen. Hang on. Add 3. And that gives me 2 times the cosine of theta is equal to negative 2. Now I'm going to divide both sides by 2. And so what I'm trying to figure out is, when will the cosine of theta be equal to negative 1? All right, so let's identify on our unit circle when that occurs. Cosine, that is the x-coordinate. And you can see right here at pi, the cosine is negative 1. So that means that theta has to equal pi. Now, notice I'm not going to put plus or minus 2 pi k because I've been given the restrictions that theta lives between 0 and 2 pi. That's the only place on my unit circle where the x-coordinate shows up as negative 1. So that's my only solution. Theta is equal to pi there. Okay, moving over here. Now, once again, we have this interval between 0 and 2 pi non-inclusive. So we start out with 2 times the sine of x plus 1 equal to 0. Proceed forward by isolating the sine of x. So I subtract 1 from both sides, and that leaves me with 2 sine x equal to negative 1. Divide both sides by 2, and the sine of x is equal to negative 1/2. So x has to be equal to, okay, so that the y-coordinate is negative 1/2 at 7 pi over 6 and at 11 pi over 6. Once again, we have to be on that interval of just moving through the circle 1 time, so those are our only 2 solutions here. So we get that x is equal to 7 pi over 6 and 11 pi over 6. Once again, easy enough for us. All right, so here we have a little statement about solving equations involving other trigonometric functions. And as you might suspect, what you basically do is attempt to put it in terms of sine and cosine, because we know we can use the unit circle once we have everything in those terms. So that's what you do. You can see we have a cosecant here and we have a tangent. So we're going to just turn those into some version of sine or cosine. And I'm just going to pull the unit circle off to the side here until I get done working on this left-hand side, and then I'll move it over to the other side. I didn't have room to stick it to the board and still be able to work the problem. So, all right, so we start out with the cosecant of theta equaling -2. And now notice we have a restriction. We want to be between 0 and 4 pi, so that means going through the circle twice. So this will be an interesting set of solutions for us. Okay, so the cosecant is the reciprocal sine function. So this is the same thing as 1 over the sine of theta equaling -2. And I'll just point out that this -2 is over 1. So since I have a proportion set up here, I can cross multiply. Now, let me warn you, cross multiplication only happens across an equal sign. So that's the only time you can use that technique. So be very careful that you don't cross multiply when you shouldn't be. And really, cross multiplication is just multiplying by the denominators kind of all in one step. So that's, oops, I grabbed my white pen again. Okay. So that's -2 sine theta equaling 1. And then to isolate sine theta, I just divide both sides by -2. And I get sine theta equal to -1/2. Okay, so let's go to our circle and identify where the y value is -1/2. And we have that occurring at 7 pi over 6. So I'll just jot down up here. We have 7 pi over 6 is one possibility. And we have 11 pi over 6. However, I need to move through the circle again. So all I do is I take each of those solutions and I add 2 pi. Well, that's really 2 pi over 1 that I'm trying to add. I need to get a common denominator, so I multiply by 6 over 6. And that has me adding 7 pi over 6 plus 12 pi over 6, which is 19 pi over 6. So I've got another solution there. And I need to do the same thing with 11 pi over 6. I add 2 pi, which is, we know is 12 pi over 6. And that gives me 23 pi over 6. Okay, so I have 4 solutions between 0 and 4 pi for this equation. So theta is equal to 7 pi over 6, 11 pi over 6, 19 pi over 6, and 23 pi over 6. There are my 4 solutions. Okay, now I'm just going to move the unit circle over here so I have room to work on the other side. All right, so I start out with the tangent of theta minus pi over 2, equaling 1. And I know that I need to stay 1 rotation in the circle because I've got 0 to 2 pi there as my domain. And I know that tangent is the same thing as the sine over the cosine. So I'm going to change that to theta minus pi over 2 divided by cosine of theta minus pi over 2. And that equals 1. All right, so since the cosine is my x-coordinate and the sine is my y-coordinate, I need to figure out when are these two things going to be equal? Because when they're equal and I divide one by the other, it's going to come out to be 1. And so if I look at my unit circle, let's see if I can grab it here. There we go. If I look at my unit circle, you can see that sine is equal to cosine at pi over 4. It also happens at 5 pi over 4. Okay, so don't forget that the tangent has a period of pi. It does not have a period of 2 pi. We studied this a few sections ago. So one thing that I need to do is say, okay, well, since I'm dealing with taking the tangent of theta minus pi over 2, let me write those two values down actually. We've got pi over 4 and we've got 5 pi over 4. Okay. So we have, we need to know, okay, well, when is theta minus pi over 2 going to be equal to pi over 4? Okay, because we know that if we take the tangent of pi over 4, we get 1. So I add pi over 2 to both sides. I get that theta equal to pi over 4. Okay, so pi over 2 is the same thing as 2 pi over 4. I just did the fractional math, getting the common denominator in my head there. And that occurs when theta is 3 pi over 4. So notice they're not asking for the actual angle that gives you a tangent equal to 1. They're saying, okay, what's that angle that I can subtract pi over 2 from and get 1? Okay, so one of my solutions is actually 3 pi over 4. All right, and then I also have the possibility of 5 pi over 4 giving a tangent equal to 1. So I also need to know, okay, well, when is theta minus pi over 2 going to be equal to 5 pi over 4? So theta equal to 5 pi over 4 plus 2 pi over 4, and that happens when theta is 7 pi over 4. So they got a little tricky on us, but it makes us think, so that's good. So our solutions for theta are actually 3 pi over 4 and 7 pi over 4. Welcome, Ken. I'm glad to have you in the room. Okay, so just a couple more to look at. So we have here the tangent of x equaling the square root of 3. And this one takes a tiny bit of cleverness. So we start out with tangent x equaling the square root of 3. Don't forget the tangent is the same thing as the sine over the cosine. So basically we're trying to figure out, when can we divide the y-coordinate of one of those points by its x-coordinate and get the square root of 3. And it took me a minute to really look through the coordinates of the point, so that's why this one's a little bit tricky. Also notice that they did not give you an interval for the domain that you have to stay between, so we're going to have to add or subtract those rotations through the period of it. And remember, the period of tangent is just pi. So actually, once we get our solution, we're going to add or subtract pi k instead of 2 pi k. All right, so here's what I discovered. When you divide square root of 3 over 2 by 1/2, you get the square root of 3. So watch this. Square root of 3 over 2 divided by 1/2 is the same thing as square root of 3 over 2 times the reciprocal 2 over 1. My 2's divide out and I get the square root of 3. So that happens when x here is equal to pi over 3. So x is equal to pi over 3, or any subsequent rotations through that period. So I have to add or subtract pi k, because the period of tangent is pi, not 2 pi. So those are my solutions for the tangent of x equaling the square root of 3. All right, this next one, Ken, hopefully you're not too lost on all of this. Hopefully it'll start making sense here in a minute. And I see you're typing something. Okay, cool. Ken says he thinks he's good. That's awesome to have come in at the point that you did and be picking up on it. Okay, so 2 times the tangent of x plus 3 equals 5 plus the tangent of x. Well, you know you've got to get that tangent of x isolated to be able to solve here. So what I actually have to start out doing is good old distribution so that I can get that tangent x as a term by itself, not being attached to that 3 inside the parentheses. So I have 2 times the tangent of x plus 6 equals 5 plus the tangent of x. Pardon me. Okay, so I can come back and I can subtract the tangent of x off of both sides, and I can subtract 6 off of both sides. And I get, so 2 tangent x minus understood 1 tangent x just leaves me with the tangent of x. And 5 minus 6 is -1. Okay, easy enough. Don't forget that the tangent is the same thing as the sine over the cosine. So the sine divided by the cosine equals -1. Let's see. So I need them to be the same values but opposite signs, and that happens at 3 pi over 4. And it also happens at 7 pi over 4. We have been given the restriction to contain us to 1 rotation through the circle, so there's no need to add or subtract pi k from that. So we just get x is equal to 3 pi over 4 and 7 pi over 4. Those are our two solutions. Okay, using your calculator. Believe it or not, this is a little trickier than you would think with just grabbing your calculator. Okay, so we start out with the secant, which we do not have a button for on our calculator. The secant of theta equaling -4. Okay, so the secant is the same thing as the reciprocal cosine. So this is 1 over the cosine of theta equaling -4. I am able, since I have a proportion set up, I'm able to cross multiply here. And that gives me -4 cosine theta equaling 1. And then I divide -4 off of both sides to get the cosine of theta equals -1/4. Well, that's not going to direct us to any of our special angles on our unit circle, so this is why they say, okay, it's time to use a calculator. Well, we know if the cosine of theta is equal to -1/4, the arc cosine of -1/4 is equal to theta. So that's how we find theta. We go to our calculator, put in arc cosine of -1/4, and we get here that theta is approximately 1.8235. However, that is not the only solution, believe it or not. I'm actually going to go and grab a diagram from your book to look at here. And it's a diagram from a problem, oh, it's actually this problem. I thought it was a problem that was just like it, because I think this will help you understand what I'm about to do to see this picture. So this was a diagram that was listed in the solutions, the explanation of the solution of this particular problem. Okay, so you can see we have the 1.8235. That's that orange angle that has its initial side on the x-axis, and its terminal side is in quadrant 2 there. And because we know that there's that potential of having another solution show up, what we do is we take pi and we subtract our initial theta angle, and that gives us the reference angle. And why we want the reference angle is because if we then proceed to add that reference angle to pi, not the number 2 pi, but if we add the reference angle with pi, that's going to give us another solution for this particular problem. So hopefully that's not too confusing to think about. So I'm going to show you how we come up with the reference angle, and you just use your calculator. So we know that theta is approximately 1.8235. And then I'm going to call this theta prime right here for that reference angle. So theta prime is equal to pi, which is that 180 degrees, pi minus the angle that I've already found. And I literally used the pi key on my calculator. I took pi minus 1.8235. And when I subtracted those, I get that that reference angle is approximately 1.3181. And now to find the other solution, I need to, okay, so they're calling that theta prime as well. I'm going to call that other angle that gives the solution, I'm going to call that theta prime prime, just to keep everything separate. So theta prime prime is equal to pi plus my reference angle, 1.3181, that puts me at that quadrant 3 angle that starts at the x-axis and goes all the way through to quadrant 3. And when I put that into my calculator, I get that my other possible solution is approximately 4.4597. Now, once again, they did not give us any restrictions with our domain. And so we need to consider that we can go through this circle as many times as we want to. And every time we hit quadrant 2, we're going to hit a solution. And every time we hit quadrant 3, we're going to hit a solution. So theta is approximately, because we did have to approximate those decimals, theta is approximately, the first one we found, 1.8235 plus or minus 2 pi k. Cosine's period is 2 pi, so that's why we add or subtract 2 pi k instead of just pi k. But then we also have the possibility of theta being approximately 4.4597 plus or minus 2 pi k. Those are the solutions for this particular problem. When the secant of theta is equal to -4. Those are your solutions. Okay, so this next one, let me just move this over some. I'll just put it up there. All right. Cosine theta equal to -0.2. All right. So since this is the cosine, I don't need to change anything. I don't need to change it into either sine or cosine because it's already there. The arc cosine of -0.2 is equal to theta. And when I put that into my calculator, I get that theta is approximately 1.7722. So that is one of my solutions, but I need to find the reference angle and add the reference angle to pi to get my other possible solution. So the first thing I'm going to do is, so this is a solution, and now I'm going to find the reference angle. So to do that, I'll call that theta prime. Theta prime is approximately pi minus 1.7722, which is approximately 1.3694. My other solution, I'll call that theta prime prime, is approximately pi plus my reference angle, which is approximately 4.5110. So my solutions for theta, I get theta is approximately 1.7722 plus 2 pi k, and theta is approximately 4.5110 plus or minus 2 pi k. Ken, how is that for you? Did that blow your mind, or were you able to follow it okay? Did the diagram help you think about that? Bring that back in here, make it a little smaller so it'll fit. And I see you're typing. Okay. Ken says he got really concerned for a minute, but he thinks he understands it okay now. All right. Well, we'll move forward then. Okay, yeah, I thought that the diagram would be helpful because I kind of had to step back for a moment and wrap my brain around it too. So it was helpful for me to see it. All right. Pardon me. Okay, so solving trigonometric equations in quadratic form. You're going to solve them just like you do regular quadratic equations. You're just going to use substitution. I usually use U for my substitution variable to stand for, you know, either cosine theta or sine theta, whatever I'm dealing with. This first one's a little more difficult than the second one because this first one does not factor, so we end up having to use the quadratic formula to solve it. The second one on the right, it does factor, so it'll be a little bit of a breath of fresh air after this first one that we do. Okay, so we start out with cosine squared theta plus 3 cosine theta minus 1 equals 0. So we're already equal to 0, so we're ready to solve. I'm going to note that I'm going to let U equal the cosine of theta. And I'm just going to rewrite it so it's not so crazy looking. That just makes this U squared plus 3U minus 1 equals 0. And the way I know that that doesn't factor, there are no factors of -1 that add to make 3. So I know I'm going to need to default to my quadratic formula. So U equals the opposite of B plus or minus the square root of B squared minus 4AC all over 2A. So U is equal to -3 plus or minus the square root of 9 plus 4 over 2. So U is equal to -3 plus or minus the square root of 13 over 2. All right. So we have a plus and a minus that we have to deal with here. Since U is equal to this thing, we now know that the cosine of theta is equal to -3 plus or minus the square root of 13 over 2. Okay, so which means the arc cosine of -3 plus or minus the square root of 13 over 2 is going to equal theta for me. Okay? So here's where it gets a little tricky to think about. When we put arc cosine of -3 plus square root 13 over 2 into our calculator. So this is for the plus one. We get that theta is approximately 1.26. Okay? Now, when we put arc cosine of -3 minus the square root of 13 divided by 2, we get an error in our calculator. And that's because the domain of arc cosine is -1 to +1. So, which is the range of our cosine. So, when we put that in, we get an error. However, there is another solution. And so what we do to find the other solution is we have to subtract the arc cosine of -3 plus the square root of 13 over 2 from 2 pi, because we're told here to stick between 0 and 2 pi. So another possibility of theta is that theta is approximately 2 pi minus, and I'm just going to write it as arc cosine of -3 plus the square root of 13 over 2. And when you put all that into your calculator, you get that that's approximately 5.02. So theta is approximately, we've got two solutions between 0 and 2 pi, 1.26 and 5.02. Those are our two solutions for theta that live in the domain between 0 and 2 pi. You all right with that, Ken? That one was a little tricky because of the error that you get when you try to take the arc cosine of -3 minus the square root of 13 over 2, but there is another solution that you have to find. So is that clear? Okay, cool. Just move that up over there. And actually, I don't know why I put oh, no, this isn't. This isn't a calculator one. Those were the last two. That's why I have a unit circle on this page. Okay, so I start out with sine squared theta equals 2 cosine theta plus 2. Okay, so when you're solving trigonometric equations like this, you don't want more than one trig function showing up. So what I'm going to do is be clever here. And what jumped out at me first was the sine squared of theta. And it triggered my memory, oh, that's one of our Pythagorean identities. So I changed sine squared theta into 1 minus cosine squared theta. And that equals 2 cosine theta plus 2. Well, now I've got a quadratic and it's all in cosine. So I need to get it equal to 0 and solve. So I'm going to add cosine squared theta to both sides. And I'm going to subtract 1 to get that all off of there. And the reason I took it that way is I don't like my leading term being negative, so that's why I put cosine squared theta on the other side. That's just personal preference. Cosine squared theta plus 2 cosine theta plus 1. All right. So now I'm going to come back and I'm going to say, okay, I don't want to see all these cosines when I'm trying to factor and use a zero product property. So I'm going to let the cosine of theta equal u. And I'm just going to rewrite this in u's. So 0 equals u squared plus 2u plus 1. And now all I need to do is figure out, okay, well, what are the factors of 1 that add to make 2. Well, that's 1 and 1. So I have that factors as u plus 1 times u plus 1, which is u plus 1 squared. So now I can use my zero product property. U plus 1 equals 0, so u equals -1. Remember, u is the cosine of theta, so when does the cosine of theta equal -1? That's where I grab my unit circle and take a look. And remember, cosine corresponds to the x value. That happens, and we do have a restriction on our domain, 1 time through the circle. That happens when theta is pi. So my solution here is theta equals pi. How's that, Ken? Okay. Ken said that one made his head hurt a little, but he's keeping up. It's basically, this section is basically putting into practice all of the identities and things you've learned about the unit circle all into one. You have to, and your algebra, you have to know how to do all of it to solve trigonometric equations. Okay, so right off the bat, I'm going to go ahead and make a substitution on this one. I'm going to go ahead and let the sine of theta equal u. So I'm going to rewrite this as 2u squared plus u equals 0. This one's nice and neat. All right. And then all I need to do is factor it. They have a GCF of u, and that leaves me with 2u plus 1 equals 0. So I can use the zero product property, which says u is equal to 0, or 2u plus 1 is equal to 0. So this makes u, I subtract 1 and then divide by 2, so that's -1/2. The sine of theta is equal to u. So I have sine theta equals 0 and sine theta equal to -1/2. All I have to do is go to my unit circle and see when is the sine of theta equal to 0. That happens at 0 degrees because my y-coordinate is 0. So here, my theta can be equal to 0. It also happens at pi when my y value is 0. Notice I'm not going all the way around and doing 2 pi because we need to stay strictly less than 2 pi. We can be equal to 0, but we're strictly less than 2 pi. So those are the only two solutions that come off of that side. And now I need to say, okay, when is my y-coordinate -1/2? So I'm going to be looking at quadrants 3 and 4 for a negative y value. And this happens when theta is equal to 7 pi over 6. And it also happens at 11 pi over 6. Those are my 4 solutions. That's it for that one. That one feels good after the last couple, huh? Okay, and I see you're typing something. True, yes, she speaks the truth. Okay, so we'll go ahead and make a substitution with this one as well. We'll say that u is going to be equal to the cosine of theta. So I have 2u squared plus u equals 0. It looks exactly like the other one, but now we're looking at cosine instead of sine. So I factor u, and I get 2u plus 1 equals 0. So I know that u ends up being 0 and u ends up being negative 1/2. So the cosine of theta equals 0. The cosine of theta equals negative 1/2. And that happens for this first one. Okay, so this is when is my x value 0? That happens at pi over 2 and at 3 pi over 2. When is my x value? Negative 1/2. That's going to be in quadrants 2 and 3. And that happens when theta is equal to 2 pi over 3, it looks like, and 4 pi over 3. So you've got 4 solutions for that one also. That's it for those two. Okay. Solving trigonometric equations. Okay, so it says, remember that the techniques we use for solving are not the same as those for verifying identities. The basic rules of algebra apply here, so opposed to rewriting one side of the identity to match the other side, in the next example we use 2 identities to simplify an equation. So we're not trying to make the sides match and prove anything, we're trying to solve it, but we're going to use identities to do so. And this first one, I hope I have enough room to fit it, at least the first line of it on here. Okay, so the first thing that I noticed was that I had cosine of one angle times the cosine of another angle. So that's cosine alpha times cosine beta. So I'm going to turn that product into a sum. And then I've got sine alpha times sine beta, and I also turn that into a sum, and when I do that, everything's going to be in cosine. And that's going to be equal to square root of 3 over 2. So this first line is going to look really intimidating and really nasty. But once we get past the first line, it's not bad at all. Okay, so according to our product to sum rule, cosine x times cosine 2x is the same thing as 1/2 times the cosine of x minus 2x plus the cosine of x plus 2x. So that's just that first term there. And now, for the second term, I have the product of the sine of 2 different angles, alpha and beta. Oh, by the way, I'm adding these things. Add. Okay, so my product to sum of sine alpha times sine beta makes this 1/2 times cosine x minus 2x minus cosine x plus 2x. And that's all equaling square root 3 over 2. Okay, so like I said, this looks really intimidating at first, but it's not bad. The first thing I'm going to do is get rid of these fractions. So I'm going to multiply this entire equation by 2. And that gets that 2 away there, the 2 there, and the 2 there. So what I really have happening is the cosine x minus 2x is negative x plus cosine of 3x plus cosine of negative x minus cosine of 3x equaling the square root of 3 over 2. Okay, let me stop there and say, how is this so far for you, Ken? Are you following? Okay. Now this is really nice right here because we have opposites. We have positive cosine 3x, negative cosine 3x. And these two are like terms. So what I have is two of those things called cosine negative x equaling square root 3 over 2. Cosine is an odd function. Since it's an odd function, the cosine of negative x is the same thing as the cosine of x, equaling square root 3 over 2. So I am going to, oh, I'm sorry, the square root of 3 is not over 2 anymore. I got rid of that when I multiplied by 2, so these should not be there. Okay, so it's just the square root of 3. 2 times the cosine of x is the square root of 3. Now I divide both sides by 2 to isolate the cosine. And get, when is the cosine of x going to equal square root 3 over 2? Now I'm ready to go to my unit circle here because that is one of my values. And so I'm looking for when is my x coordinate equal to square root 3 over 2, and that happens at pi over 6, and it also happens at 11 pi over 6. They did not specify a domain on this. Actually, I think they did, and I think I cut it off because I don't have the plus or minus 2 pi k on here. So I think I cut that part of the problem off. I apologize. So we're only going to find the solutions between 0 and 2 pi. And so this happens when x is equal to pi over 6 and 11 pi over 6. So those are our two solutions. All right. Let me just give myself a little barrier between these two problems since I ran all in this one space. Okay. So with this next one, I start out with 3 times the cosine of theta plus 3 equaling 2 sine squared theta. So once again, I've run into the issue of having a sine and a cosine in my problem. Sine squared theta is jumping out at me, so I'm going to use my Pythagorean identity to change that to 1 minus cosine squared theta. So 3 times cosine theta plus 3 equals 2 times 1 minus cosine squared theta. And now I have distribution to do. So I have 3 cosine theta plus 3 equals 2 minus 2 cosine squared theta. And since this is a quadratic, I need to get it equal to 0. So I'm going to add 2 cosine squared theta and subtract 2 from both sides. 2 cosine squared theta and subtract 2. And that gives me 2 cosine squared theta plus 3 cosine theta plus 2 equals, no, I'm subtracting, plus 1. Okay, sorry about that. Equals 0. And now I'm going to make a substitution, so I'm not looking at all these cosines. So u is equal to cosine theta. So to make this look a lot nicer, 2u squared plus 3u plus 1 equals 0. I need to use the AC method to factor. So I start with A times C equals 2. Now I'm looking for the factors of 2 that add to make 3, and that's 2 and 1. So I just rewrite, busting up that middle term. So 2u squared, I don't write plus 3u, I write plus 2u plus understood 1u plus 1 equals 0. And then I split them down the center, factor by grouping. I'm going to factor out 2u there. And when I do that, I'm left with u plus 1. The only common factor that I have on the right-hand side is a positive 1. And when I factor that out, I'm left with u plus 1, and that equals 0. So I get u plus 1 times 2u plus 1 equals 0. Now I can use my zero product property. U plus 1 equals 0. 2u plus 1 equals 0. So u is negative 1. U is negative 1/2. Okay, so remember u is the cosine of theta, so cosine theta equals negative 1. Cosine theta equals negative 1/2. The cosine of theta is negative 1 when theta is pi, and the cosine of theta is negative 1/2 when theta is equal to 2 pi over 3 and 4 pi over 3. And I just used my unit circle to get those. So those are my 3 solutions between 0 and 2 pi. Ken, how was that? Those couple for you. We've got one more just straight up equation to solve, and then we have a word problem, and then we'll be out of here. Okay, yeah, it wasn't too bad. Okay, so what we have up top says, okay, sometimes it's not possible to solve with identities that have multiple angles, such as the sine of 2x or cosine of 3x. When confronted with these, it says to recall that that represents a compression in the horizontal direction by a factor of 2. So on an interval of 2 pi, we graph 2 periods, so you're going to have more solutions than expected. And so that's a lot of words to say because this problem really isn't that bad at all. Don't let that paragraph at the top scare you. It's just saying expect, more than just 2 solutions because we've compressed it. Okay, so the first thing I noticed is that I had the cosine of a double angle on the left-hand side. So I used my double angle formula and called the cosine of 2x 1 minus 2 sine squared of x, and that equals 1/2. And that is one of our double angle formulas that we learned in section, I think that was 9.3, that we learned double angle formulas. Okay, so I'm going to multiply the whole equation by 2 just to get rid of that fraction. And so that distributes to every term in the equation. So I have 2 minus 4 sine squared x equals 1. And I'm actually going to take everything to the right-hand side because I do not like my leading term being negative like that. So I'm going to add 4 sine squared x and subtract 2 from both sides, plus 4 sine squared x minus 2. That gets everything off that left-hand side. And I have 0 equal to 4 sine squared x minus 1. Okay, so if I took the time to actually substitute u in for the sine of x, I'd have 4u squared minus 1. That's a difference of squares. That factors as 2u plus 1 times 2u minus 1. So I'm going to factor the right-hand side. I'm not going to show the substitution because I just showed it up top. So this is 2 sine x plus 1 times 2 sine x minus 1. And then I'm ready to use my zero product property now. 2 times the sine of x plus 1 equals 0. 2 times the sine of x minus 1 equals 0. So here I get the sine of x is equal to, I subtract 1 and then divide by 2. That's negative 1/2. Over here, I'm going to add 1 and divide by 2. So the sine of x is equal to positive 1/2. So basically I'm wondering, okay, when are the y values on my unit circle equal to negative 1/2 or positive 1/2? That's going to happen 4 times around the circle. So when it's equal to negative 1/2, x is equal to 7 pi over 6 and 11 pi over 6. When sine of x is equal to positive 1/2, that's when x is equal to pi over 6 and 5 pi over 6. So we have 4 solutions to that particular equation. All right, Ken, thanks for hanging in there with me past the hour mark. We've got 1 problem left, and it's a word problem, but it's not bad. Okay, so OSHA safety regulations require that the base of the ladder be placed 1 foot from the wall for every 4 feet of ladder length. Find the angle that a ladder of any length forms with the ground and the height at which the ladder touches the wall. So the angle is shown as theta in the picture, and the height is shown as b. Okay, so so this is the ladder, obviously. And so if we can figure out theta, we know the angle that the ladder needs to be from the ground. All right. So we have the adjacent side and we have the hypotenuse side. We've got A and 4A because it says every 4 feet of ladder length to every 1 foot it is from the wall. So they just used A's for that. So A, that's understood 1A for 1 foot, and there are 4 feet of ladder length. The reason we used variables is because we want to know for any size ladder. We want an expression that we can just plug in the size of the ladder and know the angle it needs to be off the ground and how high it's going to go up the wall. Okay, so if we take the cosine of theta, we know that's adjacent over hypotenuse. So we get the cosine of theta is A divided by 4A. Well, my A's divide out there, and I get that the cosine of theta is equal to 1/4. So the arc cosine of 1/4 has to equal theta. And when I put that into my calculator, and we're giving these angles in degrees, so make sure that your calculator is in degree mode for this particular problem, we get that theta is approximately 75.5 degrees. So this is the angle the ladder forms with the ground. Okay, so we have our first question answered. Now they want to know, okay, well, how high up the wall is that thing going to go? So if we want to know what side B is equal to, we can use our Pythagorean theorem, good old Pythagorean theorem. That says A squared plus B squared equals C squared. So we have side A squared plus my unknown B squared equals 4A squared. So A squared plus B squared equals 16A squared. I'm going to subtract A squared off of both sides. And I get B squared is equal to 15A squared. Take the square root of both sides. Now, I don't need to consider the negative because this is a distance we're talking about, and there's no such thing as negative distance. So I get that B is equal to A square root 15. Okay, so that is the formula. The ladder touches the wall A square root 15 feet from the ground. That's it. All right, Ken, that's all I got for you tonight. Thanks for hanging in there. Hope I didn't blow your mind too much. I appreciate you coming in tonight.